Hi, everyone. We're just here, want to welcome you. We'll start in about 5 minutes, so this is not the official start. Just wanted to let you know that you're at the right time, the right place. Testing a bit of that technology. If you can see both of us, I'm Eva and Atanas. Can you please let us know in the chat box of the GoToWebinar panel? Thanks. Great, thank you. Thanks, we wanted to test the webcams. You won't be seeing too much of our faces later on, just for now. Well, I think we can officially kick off tonight's webinar. Tonight for us, obviously. So my name is Eva, and I'm part of the marketing team of Ontotext. And the presenter tonight will be our CEO, Atanas Kyriakov, and you'll get to hear him in a bit. I just need to do my regular housekeeping items. For some of you, this might be, you might already know the drill. You're already, most of you, not most of you, all of you are muted at this point, and you will stay muted until the end of the session. You will, however, be able to sort of interact with us via the Q&A panel, and I give you a couple of seconds or minutes. You can explore the panel throughout the session, and you use the Q&A part to ask us questions. We'll get to them at the end of the session. We might not be able to answer all questions, depending on how many of you are active. And if we don't do that, we will do a follow-up in the follow-up email with the recording that we usually send after the webinar. We'll also add a Q&A part where we answer we provide answers to the questions that we haven't managed to cover during the live session. And I don't think you see my screen, probably not. Yeah, I wanted to maybe give you a props up for an upcoming webinar that we have next month that will be done in partnership with Semantic Web Company. You just see very short information about it, and I'm not going to waste time on this, but I will provide links to that webinar also in the follow-up emails. And without further ado, I will now provide Atanas with the presenting powers, and I'm personally excited to listen to him and what he'll say about the potential of knowledge graphs, the potential that knowledge graphs hold for exploring and performing inference over billions of statements from various data sets.
Thank you, Eva.
Yeah, let me just give you the presenting powers. And there you go. The floor is yours.
Do you see my screen now?
Wait a second. Yeah. Yes, I do. And I imagine the other people as well. Yeah.
Well, we have 55 people. Welcome, everyone. Thank you for your interest. So let's start, because I have some 40-something slides and some demos, and it would be great to have some time for questions for you also. So this webinar is about scalable reasoning with knowledge graphs, and we'll cover quite a lot of details on what actually takes to make this possible. To briefly introduce ourselves, I'm a founder and executive director of Ontotext, which is a semantic technology pioneer. We started year 2000, and now we are one of the leaders in this field. We are part of a slightly bigger software group in Bulgaria, listed on the Sofia Stock Exchange. Most of our R&D takes place in a little known place called Sofia in Bulgaria. That's in the south part of Europe. And most of our clients happen to be international companies, multinational companies. And we deal most of the time with their offices either in London, either in New York. So we had the chance to invest substantial efforts and money in R&D for these 20 years. And we're also part of quite a number of standardization bodies and associations which develop the next versions of these standards, be it W3C, which defines RDF and Sparkle, be it organizations like Enterprise Data Management Council, which works on more specific ontologies and different set of standards, be it the Linked Data Benchmarking Council that I'll mention later on. So that's briefly who we are. Our most popular product is Ontotext GraphDB, and we are one of the better recognized vendors in this space. According to recent market research by Brewer, we're the key player in the RDF space of the bigger graph database market. That's our portfolio. We've been doing a combination of knowledge graph management and text analysis, and we've been synergizing these two things for like 20 years. We started doing GraphDB because there was no triple store which was good enough to back our vision on how to use big knowledge graphs for text analysis. Now GraphDB is the most popular product, but it's just part of a bigger knowledge graph platform which also has provisions for text analysis, data quality management, exploration, and so on and so forth. We've been specializing in quite a number of domains, all the way from financial services, market intelligence, life sciences, healthcare. We essentially do have two lines of business. One of them is GraphDB and the platform. As products, we have quite a big number of partners which just integrate GraphDB in their solutions and in their offerings like OEM. We also do have some solutions business where we deliver knowledge graph solutions on top of these products. So let's go to the main subject. We've been doing knowledge graphs way before this term became popular, and knowledge graphs in the way we do it and the applications that we do are mostly about putting rich data and diverse data in context. And knowledge graphs help essentially in two ways. On the one hand, they allow you to link data across different data sets, and also you can have semantic schema and semantic metadata to describe these data so that both humans and machines can interpret them. And what our technology is tuned for and what the kind of reasoning I will present is tuned for is what happens when you merge multiple databases, when you also get some additional information extracted from text and some metadata related documents. And it's even more interesting when you merge proprietary information and proprietary databases with big external global data sets that are also integrated in knowledge graph to give you even better context and allow better insights and analytics. That's roughly a very brief story on what we are doing. Now, our definition of the knowledge graphs, which happen to be somewhere on top of what is knowledge graph in Google, is that's essentially a collection of interlinked descriptions of concepts and entities. And the magic here is that essentially through this high level of interrelationship between the different concepts and entities, you get to the point where concepts describe each other and provide context to each other. And at the end of the day, this allows better interpretation of the data that you have in there. In a way, knowledge graphs can be seen as a combination of three well-established paradigms in computer science. One of them is database engines and structured querying, and you can definitely do that with knowledge graphs. Then the other aspect is that, well, these are big network structures, and you can do what people do with network structures, like do analytics, the kind of analytics Google does to determine how important a page on the web is based on who refers to it. And then the third thing, and that's the topic of this seminar today, is you can see a knowledge graph as a knowledge base or an expert system. If you think in the terms of the 80s or the early 90s, and do reasoning and infer new facts. And you can see the example on the right of, let me just minimize, on the right, that in a graph like that, you can have some information about companies like Big Bucks Cafe controlling Global Investment Inc., which controls my local cafe, and then you can have this linked to some geographic information saying, well, Big Bucks Cafe is located in Seattle, and the Global Investment Inc. is in West Bay, and my local cafe is in New York, and then some further information telling you that Seattle and New York are part of whatever states, and which are part of US. Okay, the dashed arrows, what you see as dashed orange arrows here are statements that the database engine can infer for you. So if you know that Big Bucks Cafe is located in Seattle, and Seattle is part of Washington, Washington is part of USA, given the right schema and the right semantics behind it, the engine can infer that Big Bucks Cafe is located in Washington, and it's located also in the USA, and the same for the other companies. And this way, through inference, you can add more statements, more relationships to what you already have in the knowledge graph. And this is sometimes quite often very useful, because you can easily find multi-hop relationships. You can find patterns that would otherwise be very slow to find. Like if you're searching for patterns like give me companies in US that control another company in US through a company in an offshore zone, you can do this with many different databases. But putting the data together and executing this query is quite much easier and more straightforward and faster with the graph database with inference as compared to most of the other approaches. And this is essentially the kind of scenario, the driving scenario behind most of the inference that we have implemented through the years. Now, how stuff works? Well, the important thing about doing knowledge graphs and doing graphs with formal semantics using the Semantic Web Standards like RDF schema and OWL is that you can have a semantic schema which provides formal semantics of the different classes and types of relationships, and also special relationships that you can have between each resource and each concept. You can see this example. On it, you can have a schema part of the graph, and in graph databases you have all types of data together. You have the green part, like the class hierarchy, woman being subclass of person, being subclass of agent, definitions of some relationships like child of, parent of, relative of, and so on and so forth. And you can also have the very specific instance data in there, like the fact that is probably asserted from some other data source, imported from some other data source, that Ivan is child of Maria. So once you have all this in the graph database, you can let it do inference. And in this specific case, again, you see with dashed arrows everything that GraphDB and other engines can infer based on what you have from the explicit facts. Those edges which are with bold lines, non-dashed. So the trivial example is that whenever you have a woman subclass of person, subclass of agent, the engine would infer that, well, okay, woman is also subclass of agent, so going up the hierarchy, because subclass of is defined as a transitive property. Then the more interesting part is once you have this, and if you know that Maria is instance of woman, you have this relationship Maria type woman. Because of these subclass relationships, there is a rule in RDFS which will let the engine automatically infer that Maria is also person, Maria is also agent. That's not rocket science on its own. That's essentially encoding the very basic object-oriented semantics using logic and rules. To go to the next step, you have this relationship saying Ivan is child of Maria. And then in your schema, you can have the semantics of child of described, so that you say, well, it is inverse of parent of. And then you can also say that parent of is a special case of relative of. And you can also say that, well, by the way, relative of is a symmetric property, which means that if A is relative to B, then B is relative to A, and so on and so forth. So with this simple schema telling you that child is inverse of property parent and parent is special case of relative of, you can already get quite a number of benefits. Being able to infer that, well, Maria is parent of Ivan, which is the inverse relationship, and then that you have a relative of relationship which goes both ways. This example is intentionally simple. Most of the time I'm getting criticized that it's not simple, but yeah, it is simple because we have two relationships and a couple of objects and three classes. What is important to mention here is that when you define the semantics in your schema, you should be minimalistic. So you should define as little as possible to get your job done. So obviously in parentship and being child of someone, there is much more involved compared to what we have provided in this schema. So it's not just about being inverse to one another and being special case of relative of. In the real world, there are plenty of other things that you may want to say about these relationships. But most of the time in ontologies, we keep them as simple as possible and define only the semantics that is relevant to our applications. So why we do this? What's the benefit? Well, one direct example is, imagine that you merge data from multiple sources and you need to align their schemata, because when modeling one of the sources, the DBA or whoever, the architect who modeled it, decided that they will use parent of relationship to link parent to child. And then in the other database, someone decided to use child of, which is just the inverse one. And you have a third source, which is less granular and less picky about the different type of relationships in a family, and there is just a relative of, and that's it. Now, when you put this data together, sometimes it can get hard to trace all the schema notions and the data modeling patterns used by the different sources. So what we achieve with reasoning when you relate when you align the different relationship types and primitives coming from different schemata, is that you can have a query that has a simple pattern in it, like give me all x's which match the pattern Maria relative of x, and then it will match Ivan. Although in the very specific case from where it comes from, you have a different relationship, child of, and it goes in the opposite direction. So with this trivial example, you see that even such simple semantics and couple of rules can help you, can make it much simpler to query data disregarding the directions of the relationships and the different modeling patterns that could be used across different sources. And that's very important when you combine data from multiple sources. Then the other thing is obviously that Using inference, you can detect patterns in a better way and get deeper relationships, because you have an engine which expands all relationships and finds relationships that require some recursive investigation or traversing, and that's not what the database engines do query time. They most of the time get what they see. If in a big database you start doing recursive querying, it gets really slow. With reasoning, you can get the benefits of tracing multi-hop relationships, combined with the benefits of having an efficient database engine where you can do a query with 10 joins and get the results in a second. And of course, you can use reasoning to also do consistency checking and quality validation and so on and so forth, just to make sure that your data is right. Well, that's essentially the reason why these benefits are the reason why people were trying to use reasoning in various systems for many years. In the most recent history, 20 years, and you can go much further back if you go into the roots of mathematical logic. But most of the time, when you get these experiments on a big scale, they fail. I mean, some of you can recall probably projects like Psych, which were trying to model the knowledge of a 7-year-old kid with formal semantics. So there is this balance. If an ontology is too small or a knowledge graph is too small, it's not fun. I mean, there are not many things that you can infer out of it. If it's too big, then you should deal with context, and it becomes really tricky. But in a typical project, most of the reasons why we see projects and architectures and approaches using reasoning to fail, and there were plenty of those, I gotta be honest, is that people make mistakes. And one typical mistake is just over-engineering the ontology. You get someone with a PhD in logic, and then at some point it's more important to show how expressive ontology we can do, rather than thinking of what the implications will be down the road for the project. So that's a very typical mistake. The other thing is that quite often people prefer to use expressive reasoning and like say I will use RDFS or I will use swirl just because they like the extra power, without understanding the performance implications and the design choices that are needed to support such expressive languages. Another thing that happens quite often is also that well, people get misled. You get to an engine that does support the inference, and then the marketing of the company is very vocal about virtualization, without telling you that these two things actually doesn't work well together. And going this route, you can very easily spoil a project just because inference doesn't work with virtualization, and you were misled to think so. So that's what we've seen, and we've seen many years, many projects over these 20 years to fail for each of these reasons. So I want to give you some positive examples now. One of the more interesting ones that we did historically was with the British Museum, and we used an ontology called the CDOC-CRM to help them model all the information that they have about their collection, the artifacts that they have in the British Museum. And it's a very detailed ontology. That's what people in cultural heritage and generally librarians tend to do when they have the chance to. So for the fundamental relationship that one artifact is related to one geographical place, there are a very big number of variations of different ways in which the artifact could be related to the place because it was exposed there, because it was created there, because the artist who did it was from this place, and so on and so forth. If you dig into it, there are really plenty of different relationships. So one thing that this CDOC CRM ontology does is that it has the semantics to generalize, so that whenever you want, you can just make a query. I want to search for paintings which are from Geneva. Doesn't matter which of these 40 different ways of having a relationship between the painting and Geneva is actually in place, or without having to write all these 40 different parts in your query, which would be nasty. So this was the case with British Museum. They are a wonderful museum. They have like 2 million artifacts described with about 200 million statements. So they have about 100 statements per artifact. So the explicit statements that we have when we wrote this collection described this way with this ontology is about 200 million statements in the database. When you run inference on it, it expands 4 times, so it becomes close to 1 billion triples with all the inference statements that you can do in this complex structure. And that's something, actually, an experiment that we did back in 2012, I believe, on much weaker hardware, and it was still something that happens in 24 hours, depending on the configuration. To give you a different example, we did a very interesting project with BBC when they invented their dynamic semantic publishing concept back in 2010. And it's essentially about describing different materials that BBC works with, like text, publications, pictures, videos, having rich descriptions, rich metadata about this content, and then be able to generate thematic web pages about specific players or events, and so on and so forth. So that's what it actually is. And it became this pattern became essentially provided the basics for one of the benchmarks within the Linked Data Benchmarking Council. The research organization, which includes all the major graph database vendors, so all the RDF players, as well as property graph people. And we gathered there to define different benchmarks. The one that I'm mentioning here is the semantic publishing benchmark based on this pattern of BBC, which have essentially 2 workloads. On the one hand, you have updates, which are coming through the editorial staff, pushing more data into the repository, and then you have aggregation queries, which are essentially invoked each time when someone goes to the website of BBC and wants to get the page for Lionel Messi and see all sorts of relevant information. This happens through like 5 queries which are fired to the database to get different types of information relevant to this player, and a web page is generated. So the reason to tell this story is that well, benchmarks are good because, well, it is based on a real usage scenario, but it also allows you to experiment and make it repeatable and see how it scales and so on and so forth. So in this case, we scaled this scenario to a data set which have DBPD and geonames in the middle, but most of it is essentially descriptions of about 8 million different pieces, creative works, pieces of content. So this data set is 250 million statements, 256 million statements, explicit ones, and the way it does require inference to get the queries right, and that's also the the setup in which BBC was using it and is still using it 10 years later. So when you perform reasoning on top of this 250 million, you you get another 250 million statements inferred. So the actual data that GraphDB plays with in this case is 500 million statements. And you can see that reasoning is the kind of reasoning choices that we make are viable even in the case of very transactional environment where you can have like I don't know 10 agents, 8 agents that are currently trying to fetch some information to do aggregation queries to populate a page on the website of BBC. And then you have another 8 agents which are updating the database at the very same time. And then you can get on a very basic machine 50 something queries, read queries served this way, and 10 update transactions served this way, with all the inference that should happen on these 500 million triples meanwhile. That's why it is an interesting example of a very live, real application where you have reasoning involved in a very challenging database workload scenario. Another example of inference is what we have in a demonstrator called FactForge. It's again few of the popular linked open datasets like DBPD and geonames, with all the same as links between DBPD and geonames, which are 500,000 statements just like this. And then a few other datasets. We also have massive amount of news metadata in this demonstrator, because we process some 2,000 articles a day, and we do name entity recognition on top of them, and we store this metadata again in the repository. So we end up with a repository where you have 2.2 billion explicit statements, 1 billion of which is metadata about the news, and then the rest of it is what you see in the table. And again, you have quite a lot of inference taking place on top of it. So in the very same repository, we have 328 million inferred data. I will do a quick demo with this one. Just a second. No, I'm not demoing with Facebook. Sorry. FactForge. So you can play with it yourself at factforge.net. So you have this repository with you see the statistics about it. That's what I was just telling you. 2.5 billion statements, of which 2.2 explicit and whatever number inferred statements. So we have a number of sample queries to play with. One of them is the example that I gave you just before. So essentially query of suspicious control chain to an offshore company. So we also use the Fibo ontology here to map data across different data sets. So the query essentially says, I need company 1, which controls company 2, and company 2, which controls company 3. And then you want company 1 and company 2 to be in one and the same country. And then you want country 2, company 2 to be in country 2, which is in a place which has some offshore provision. So this query is as simple as it is. It runs on these 2 billion triples. We got results in 0.2 seconds. And well, because most of the time people don't put offshore companies in their Wikipedia profiles, we don't get that many patterns. We get patterns like Bertelsmann controlling RTL2, both companies in Germany, throughout the RTL group, which is registered in Luxembourg, which is actually well known as a place having offshore provisions. But that's an example of how this example in the beginning can work in a really fast manner on top of a big graph. What you also see is that actually here we see we have a single relationship controls from Fibo between the companies, and it because of the mappings that we have between these control relationships and control relationship information across different sources, we can get these answers without having to make a query with quite a number of alternative properties that may take place, which would be really hard to write as a query, and also it would be slow to execute. So if you want to try this query without inference, of course, it will get 0 results, and that's very easy to play with and without in GraphDB. So I'll carry ahead. I already mentioned Fibo. Fibo is the acronym for the Financial Industry Business Ontology developed by the Enterprise Data Management Council that we happen to be a member of. Yeah, it's an effort for the related transparency and to allow financial institutions to have a common language and common reference structure to report against, and so on and so forth. So we experimented. We've been a part of this Fibo effort and group for probably more than 5 years now, and that's statistics from one of the earlier versions. If you get 2 of the modules of Fibo, the foundations and the business entities, and you use AutoRL to reason with them, you from about 5,000–6,000 statements, which is these specific modules of Fibo, you infer another 10,000 statements, and this happens really quick. I can give you a quick demo of how this works. We can create a new repository. Sorry, test 1. We can choose a dataset. Later on, I'll tell you about the difference between different datasets. And then we just create it, and then we make it the default repository, and then we can import whatever RDF files. We go to the foundations module of Fibo, and that's I don't know, 20 files. We want also to get in this case the business entities. We get them added. We can import them one by one, but we can also import them all at once. And then yeah, whatever the delay is, it's actually the communication with the front end. If you run it directly on command line, it's a couple of seconds. So you see that this new repository was loaded with was loaded with 5,000 inferred statements, explicit statements, which is what came out of these 30-something files that we parsed, and we got another 12–13,000 statements inferred. And we also have all the means to export this data. So here you see that from these 2 modules of Fibo alone, we imported 335 classes. And then you see that they fit into 2 big groups. One is think in row, which is quite philosophical abstraction, and the other is autonomous agent. Let's say we want to dig into the autonomous agent, and then with these nested circles, you see all the subclasses of autonomous agent, which happen to be quite a number of other things, but one of them is organization. And you can further drill down and see what types of organizations you can find in Fibo, like corporation, partnership, whatever else. I won't spend more time here, but that's just a demonstration that actually reasoning could be very straightforward if you're careful on the engine that you use and the reasoning language, and the ontologies are thought out to work properly with this reasoning setup. What we did was actually that we put together Fibo with this bigger demonstrator with the 2 billion triples, and what we did was essentially to map Fibo to an ontology that we've been using to tie up these different datasets, and it was a very basic mapping. If you want, we only cared of mapping things related to public companies and control relationships. So we did all these mappings that, like, free-base business issuer is a more specific case of public company, and Proton public company is subclass of publicly held company in Fibo, and so on and so forth. So you can map a specific source to an ontology like Fibo with, if you want, seven statements. If public companies is everything that you care about, then you can insert these mappings into the database. If you're dealing with the knowledge graph that is 2 billion statements, it can take 4 hours to get it digested. But at the end of the day, you get the combination of both worlds. So if I switch to the other repository here, you can experiment with such class hierarchies and see examples and so on and so forth. In this case, it would need some time to get updated. Anyway, let's use the remaining time to walk you through essentially some the different types of reasoning ontology languages and schema languages that could be used, and the reasoning choices. So in the stack of Semantic Web Standards, OWL is the ontology language, and RDFS is the RDF schema language, which is a much simpler one. Essentially, the baseline is that well, these languages use different types of logics. Some of them go towards description logics, and some of them use logic programming, like in Power. The kind of baseline when you choose your language should be that description logic doesn't scale. I love description logics if you want, like, intellectually. I've been teaching description logics in the Sofia University back in the 90s. But at the root of it, the algorithms which should be used for inference there are based on satisfiability checking. So to check whether something is true or not, you should try to build a model which proves that the opposite is not right. That this brings enormous power, but when you have a big knowledge graph, for trying to build a model to in order to fail, in order to prove that something is subclass of something else, is really slow thing. It works when you have a ontology or some taxonomy of a few hundred things or few thousand things, and when you go to the billions, it just doesn't work, because the complexity pattern is the complexity goes exponentially. Rule-based reasoning, on the other hand, if you are again careful about what fragments you're using, is tractable. So it is it grows in polynomial time with the size of the data, which could be a problem again, but it's way better as compared to description logics. And all the examples that you've seen above, you see that you can work with really big knowledge graphs with rule-based inference, and this is just not applicable with description logics. So the two different ways in which this could be implemented, in principle, reasoning could be implemented in a reasoner or a database, is using forward chaining or backward chaining. The forward chaining essentially says, let's start with the data and infer everything that could be inferred and store it in the knowledge base, in the database. So each time the data is loaded or updated, we have to do this work to materialize, is the technical expression, to infer and store everything that could be inferred. So there are pitfalls in this also, but if it's done in a conscious manner, it scales quite well and it delivers quite manageable performance, predictable performance. The alternative to this, which actually allows more complex reasoning, is backward chaining. So in this case, reasoning is performed query time. And that's good with respect to updates, because when you load data or update data, no reasoning takes place. But yeah, there are some drawbacks which are really important to understand. There are two ways to implement it. One way through backward chaining, what actually each provoke engine does, and the other way is through query rewriting. The biggest problem with backward chaining is that imagine you start evaluating a big Sparkle query, against a Sparkle query with 10 or 12 different patterns. In the database terms, that's joins between. In the past, it was joins between tables. Nowadays, it joins between patterns in the graph. So the way in which databases work is that for a query to be properly evaluated on a big data set, you need a very specially optimized query plan, which starts with the right pattern that returns the smallest number of results. Otherwise, the query evaluation in any database that you know, like SQL database or property graphs or RDF, any of the databases that use these structured languages will fail. It will be so slow that it will never finish on a big graph if you don't have optimization. The problem with backward chaining is that query time, when you have to make the decision which pattern to start with, you don't have the statistics, because you only have the statistics when you do the reasoning, and reasoning is part of the evaluation. So essentially, backward chaining is post optimization, which causes troubles with query evaluations on big data sets. And we had many clients coming to us because they have started with an engine that does backward chaining. The initial test went okay on small data sets, and then when they scaled it up, it just turned out that query performance is awful and they can't continue this way. So that's a very typical pitfall. If you do the same query time reasoning with query rewriting, what you do is that you should query time automatically expand the patterns. Like, imagine you have a pattern in the query that says, I have variable A, which should represent something that is instance of person. So it should be RDF type person. And then you have an ontology where person has some subclasses, like man and woman or worker, whatever. And then you also have some relationships and so on and so forth. So if you have to do this reasoning through query expansion, you have to expand this single pattern into this more complex expression underneath. So you need to check in the database for all direct mentions that this resource is of type person. You should check whether there is a property which has range person and A appears in object position, or and so on and so forth, quite a number of different options. In the interest of time, I won't explain all of it. The key thing here is that, well, query writing results in a query that could be easily 20 times more complex than the original one. And then obviously it gets slow. I won't do introduction to GraphDB. We have separate webinars and you can read a lot about it on the web. So just skip this part. And I'll finish up with how we do reasoning in GraphDB. So we do use forward chaining. We use materialization. This allows us to make all these demonstrations and to do reasoning with big data sets, even in the cases when you have very high update rates, like the scenario of BBC. Reasoning works incremental in both directions. So when you insert new data, instant reasoning takes place to infer whatever new facts should be added and can be inferred with the new information. And the same works on delete. So we can figure out what should be retracted. The reasoning works with a bunch of rules, which they may look a bit ugly, but when you look into it, it's like imagine that you have P being a functional property. Then this means that this property can have a single value, like primary country for a company. If it's primary, you want it to have a single value. So if you have a functional property and then you have X related with this property to two different things, Y and Z, then according to the OWL semantics, you should infer, the engine should infer that these two things are actually one and the same thing, because if they both appear to be related with X through this property, they should refer to the same object in the real world, so they're related with this OWL same-as relationship. And then there are also consistency rules, which essentially tell you if the body of the rule, what is on top, is satisfied. So if you have X same as Y, and at the same time you have X different from Y, this shouldn't happen. So this means that we have inconsistency in the database and it should be immediately reported. Transactions should be rolled back and so on and so forth. So reasoning can go both ways, to infer new facts and to do consistency checks and to fire alarms when they fail. We do have support for we have a number of built-in rule sets which support specifications like RDFS, OWL, Autotext, as well as few specific data rule sets that we find useful, like our host. One can define custom rule sets also, and you can easily start with one of the existing ones, for instance, and remove some of the rules that you don't care about in order to improve the performance. That's perfectly okay. You can also optimize your rule set by analysis using we have a sort of optimizer and profiler, which helps you build an optimally performing rule set. You can use many of those, and you recently with GraphDB 9.2, we added a plugin which provides explanation. So you see an implicit statement that was inferred, and you can get the chain of rules that were used and what other facts were used to infer this one. So you get provenance, you get explanation. So this is the full set of rule sets that we support. You can see them all explained in the documentation of GraphDB. You just go there and you have very thorough documentation with how the rule sets look like and what are the standard rule sets that we support. So I will not dive into this now. For all the rule sets, you have optimized versions of the rule sets. So if we go here and we go to a repository setup and we create a new repository, you can choose a rule set. And you see that you can choose from RDFS, Auchorst, whatever. And then you have also the optimized versions. The optimized versions actually remove one RDFS, one of the rules, nominal rules from the RDFS semantics, which says if there is whatever assertion in the graph, like X is related to Y with property A, then we should infer for each these three placeholders that they are of type RDF resource. Well, logically, it probably makes sense for the people who have defined it, but I haven't seen an application where this is useful. No one. And this single rule has quite a lot of impact on graph database, on knowledge graphs with inference, because it actually, for each node in the graph, it will infer one more, for most of the applications, useless implicit statement. That's why we have these optimized versions to allow people to optimize the performance if they want to. You can stay with compliant with the non-optimized versions. So that's enough about it. I won't spend time with how we do inference, how we do retraction. That's our special sauce. That's a very unique feature of GraphDB, being able to dynamically retract infer statements. That's what differentiates us from Oracle and other vendors who also use materialization. We have special optimizations which make our same as, which essentially links to identifiers about one and the same object, work right. Yeah, we finished the time, so I'll stop here. We'll provide you with the slide deck anyway. You can experiment yourself and play with reasoning at FactForge.net, and we have a few other demonstrators. And I will stop here so that we can answer some questions. Yeah.
There are a bunch of questions. I also typed one for myself.
Wow.
But let's go with people's questions first. Actually, this also, I had a similar question to take you back to the pitfalls of reasoning. You mentioned that inferencing doesn't work with the virtualization. Can you maybe elaborate on that a little bit?
Well, the problem is that in order to do scalable reasoning, you should we saw that query time reasoning doesn't work. And if you have virtualization, which means that some of the data is in a remote system and you can't pre-index them, you can't essentially do their inferred closure. You cannot do the inference for them load time, because the essence of virtualization is that you don't load the data. So your database engine, your reasoner, never sees all the data. So this means that if you use virtualization, you should resort to query time reasoning. And query time reasoning just doesn't work on big datasets because you can't optimize the queries. As simple as that.
Okay, makes sense.
I don't know whether it's simple, but yeah.
Okay, do you, because well, questions keep coming. I'm not sure if you see them. Do you see them?
No, actually, I don't see them.
Okay, so let's go over. There's one very, I don't know how to categorize that question about the future of Shaco.
Okay.
So do you have any thoughts on that? What might be the future of Shaco, like, and where does it fit on our graph's complexity versus rule-based reasoning?
Okay, so well, Shaco, we have Shaco is one of the standards, actually the most popular standard for RDF shapes, which are used for validation. So we have implemented Shaco support I think at the end of the last year, and yeah, I see it like something getting wider adoption, because quite often you have kind of constraints or validation rules that you don't want to put in your ontology, like in your RDFS schema or our ontology, which is like syntactic checking or different constraint checking, for which really OWL is not a good option, while Shaco and Shex are really languages that are properly taught out to support this. So yes, I see good future for Shaco.
Okay, hope that satisfies whoever answered that, asked that question. Well, questions keep coming. I'm going on to the next one, which is a bit more specific. This person is using a breadth search algorithm to extract all neighbors of an instance through 20 hops. By hops, I imagine that they mean, what is it?
Yeah, okay.
Yeah,
I understand the question. So,
in the
well,
wiki.
that's not necessarily about a reasoning problem. That's the problem for searching a path in a graph. And the reasoning can help here by materializing some relationships and transitive relationships to make to make some shortcuts so that you can quicker find a shorter path between these between the nodes. But itself, it's not about breadth search or depth first search.
Okay, and they ask if that's possible in GraphDB, or whether they need a cluster to distribute the queries, or how fast is the process, but I guess it depends.
Well, reasoning is supported in all versions of GraphDB. You don't need a cluster. You see the different versions of GraphDB. We have free version, free edition, standard edition, and enterprise edition. And RDFS and OWL reasoning are supported in all GraphDB editions. So even with the free version, you are free to go. The only limitation is that if you go with the free version, you actually have you don't take the benefits of our parallelized inference. So inference would be a bit slower. You can easily see this if we go to just a second.
You might need to share. Do I see your screen?
Isn't it sharing
yeah,
now?
I see it. Yeah, I see it. Yes.
So you see here we benchmarked. There is a web page on benchmark results for GraphDB, so you can go and see there. We have benchmarked what it takes to load these 250 million triples of the linked data benchmarking council's SPB benchmark that I presented to you. So if you use RDFS plus rule set on GraphDB free, it will take on a really slow machine. Sorry, this is seconds. That's not minutes. It will take. No, it is minutes. it will take as much as 500 minutes, so a bit less than 10 hours. And if you use the enterprise version or the standard version, SE or EE, and you have a machine with multiple cores, you can get the inference done twice faster. But beyond that, yeah, inference works well. And here is an example also of why you should choose the rule set carefully. You see that reasoning on this fairly big data set actually takes 500 minutes with RDFS plus. And if you go to Auto RL, it can take almost 3 times longer, or 2 times longer, 2.5 times longer with the Enterprise Edition. So you should never use a reasoning profile or rule set that is more complex than what you actually need, because it's just a waste of performance, a waste of effort.
Okay, maybe one more question. There's one about future plans, whether we plan to support Sparkle-based inference languages like Spin. And I admit I'm not really familiar with that one.
Well, Spin is a very good language, which was developed by Top Quadrant. The reason why we don't provide support for it is that well, it is very expressive one, so it works well if you have to manage some taxonomies and ontologies, and if you deal with thousands of things. But that's one of these languages that doesn't scale well if you have to deal with millions of things. Mm-hmm. So we have concerns about the scalability. We have a very efficient and very flexible Sparkle engine, obviously. So implementing it is relatively straightforward, but yeah, we just don't believe, we generally don't implement things which could be misleading in terms of performance. So we are trying to prevent users from going into something that can break their project down the road. So I see some of the questions now. So
okay,
I finally found them.
I don't know if you have time for more questions. If you do, go ahead. And if not, we can wrap this up and maybe go over, not maybe, but obviously there are some more questions that we will address in the follow-up email. So it's up to you and your time, actually.
Yeah, so everyone is free to leave. Of course, we can't keep you on the webinar. I'll answer a few of the more relevant questions that I imagine will concern many people. So there is a question about saying in GraphDB. That's a question from Freddy Limpens. I hope I pronounced the name right. In GraphDB, when you do an update, do you apply inference after delete, then once again after insert, or do you wait the tool to be finished? We perform inference at the end of the transaction, so we wait for all the changes to take place, and we only after that we delete what should be deleted and we add what should be added. But this all happens in a transparent manner, so the people doesn't need to care about it. It is fully automatic. Okay, let me see whether we have some other questions. Sometimes we have there is a question from Jay Craig. Sometimes we have to convince management or customers to explore this approach. Sorry, which approach? Can you provide a simple, interesting example, maybe considering the first example of the firm relationships with offshoring, of how the software tools uncover something hard to find without it? Well, what I provided as example in FactForge was one of them. We can connect to you and provide you with some further examples. Yes, there are plenty. Okay. I see a question saying, what questions keep coming?
Yeah, they keep coming. Some of them are more like comments as well. Okay, I have a question. It can be a dumb one, but so again, take you back to the reasoning pitfalls. You mentioned that reasoning wouldn't work okay both with like knowledge graph that is like too big, that contains way too many statements, and one that has a very basic ontology. So is there like a number, like an appropriate size, I don't know, appropriate number of statements where reasoning can perform best, or it depends?
Well, okay, it's not actually about the sheer size of the database.
Okay.
It's more about the connectivity patterns and the semantics that you provided to the database engine. I can give a simple example when even with the simplest possible AUF fragment, you can break the engine. Think of the relationship fellow citizen. So someone being a citizen of the same city as somebody else. Then think of a city with 1 million citizens,
Yeah.
which are somehow related to one another with, each of them is, imagine that they're initially, that's artificial example, but they could be initially related with citizen A is fellow citizen of citizen 2, which is fellow citizen of citizen 3, and so on and so forth. So you can have all them related in a list, and if you put this in a database, you have 1 million, okay, actually 999,999 relationships between them. And then the semantics of this relationship fellow citizen is that it is transitive and it is symmetric. This means that if I'm a fellow citizen with you, Eva, then you fellow citizen with me, because it is a symmetric relationship. It always goes both ways. And it's transitive because if I am fellow citizen with you and you're a fellow citizen with Ivan, then I'm also fellow citizen with Ivan. And it's transitive. Then in this example of 1 million fellow citizens, if you apply inference and you do all the possible relationships that you can infer this way, you will end up with everyone in this city being related to everyone in this city, right? Which is good because they're all in the same city. But then you have 1 million citizens, each of them with 1 million relationships to each of its other fellow citizens. This is altogether 1 trillion relationships. So this is a simple example how you don't have to go into the billions to get in trouble. You can get in trouble with mid-size graph with 1 million relationships, which, if you're not cautious about the semantics you put in there, can easily explode into a gigantic 1 trillion knowledge graph out of nothing. So that's, I mean, reasoning is a powerful thing, but as many things with the database engines, one should be careful about it, and also, yeah, some testing and making sample cases, benchmarking always helps to find potential issues where you get the kind of inference that is not what you meant, or something that you haven't predicted in the beginning, but causes a trouble and you gotta fix it. But that's not typical with databases. That's always the case of being cautious about your database schema, and with knowledge graph you have to be cautious about your ontology and the semantic schema that you have in order to avoid performance issues. But it's not the sheer size, it's like also about the performance of the SPARQL queries. You can
so
make
quite
a
so many
dump
pitfalls by now.
you can write a dump query even against a small repository, and it can work forever, because for instance you have a Cartesian product in it and you have unrelated patterns, and you have 1,000 matches for one of the patterns and 1,000 matches for the other pattern, and then out of a sudden you have arbitrary 1 million potential bindings just because the query is not right. So if the query makes sense, it would evaluate more or less in the same speed. Doesn't matter whether you're dealing with a knowledge graph of 1 million statements or a knowledge graph with 10 billion statements. It would be just a little bit slower on the bigger one, but the order of magnitude will be the same. And the same is with inference. If you don't do stupid things, you can scale very far.
Okay. Well, that
So
was
for most of the projects that I've seen, the scalability was not the issue. It was whenever you have to reissue it, issue with the ontology, with the schema. But we are always willing to help. We have a very strong support team which handles this kind of why I'm not getting what I expect from this inference. We're getting such questions 24 hours a day, and we answer 99.9% of them. So don't hesitate to come to us and ask why the inference doesn't work as expected, or what you can recommend. We have an entire team that deals with these type of questions, and they will never tell you that you're stupid.
That renders perhaps the need for a follow-up webinar that focuses again on reasoning and goes further into depth. Okay, I think we can end it with this, unless you want to go further with the questions, but I see that there are not so many coming in. I think we're good. Okay, what do you think, Naso?
Yeah. I don't see other questions that can be answered directly. There is the one about the examples of jQuery. Yeah. We will provide some examples. How do you import data in the database and align a DB schema to DB graph? I fail to understand these questions, so we can reach out to Mandeep Singh and discuss it.
Okay. Well, I think I should wrap up now.
Yes,
for
please.
the few people, people who are still with us, and I want to thank you first of all for carrying out the session, and then thank you to everybody who stayed and participated and listened. And you already know that we'll follow up this live session with a email in which we'll add link to the recording, the slide deck, some extra additional information about our upcoming webinar with Semantic Web Company, and address some of the questions that we didn't cover today. And yeah, Thank you, and see you again hopefully soon. Bye.
Thank you. Thank you very much for staying with us. Bye-bye.